And in fact, when I started to work on social systems as a physicist, there was no field called sociophysics at that time. And later on, when I worked at ETH Zurich as professor of sociology, in particular of modeling and simulation, there was no field called computational social science. Until there was this publication in Science in 2009, and now my professorship obviously is called computational social science. So we can see really this evolution of science, new fields are coming up, and this wonderful conference in Finland last year, organized by Santo Fortunato with more than 500 participants, really shows that there is an explosion of this field. As it was said, this is not only because, of course, we can simulate complex systems much better, but also there's now much more data that allows us to calibrate those models. Now, classically, we've been thinking about threats to our society as coming from the outside. Now, like comets hitting the Earth. I think we need to turn off the other microphone.
I'm sorry?
Comets hitting the...
No.
Comets...
Yes.
All right, so we've been thinking about threats to society as coming from the outside. Comets hitting the Earth, but also tsunamis, volcano outbreaks, hurricanes, and all this. Now, these are old problems. The new problems are coming from the inside of society, that are a result of systemic instabilities, and this includes financial, economic, and debt crisis, social and political instabilities, environmental and climate change, organized crime, cybercrime, the quick spreading of emerging diseases, and also this point of climate change really requires our particular attention, because it's threatening about 1/6 of all species on Earth. That means our entire ecosystem might dramatically change, and it's threatening also the future of humanity. It's not clear what is actually the carrying capacity of this planet in the post-carbon economy. So we're literally struggling for survival. We just haven't noticed yet. And that means that science doesn't only have to make a contribution to a better understanding of this world and our society. We have to change our society, otherwise many of us may not survive this. And also, Sandy Pendleton and Geoffrey West have pointed that out many times. We cannot anymore do business as usual. These crises that we're seeing create a large collateral damage. It costs our society billions every year. The financial crisis itself has cost about losses of about 14,000 billions. And this is not the only problem that we are struggling with. So this requires a new approach and actually a new science, and we call this global systems science. So as you can see, this paper was published in Nature. And what is global systems science about? Well, it recognizes that humans have created tightly connected systems and network risks. And with this, a world that we do not understand and cannot control well. We need to change our perspective on the world from a component-oriented view to an interaction and network-oriented view. And basically, global systems science is there to help us to understand information society and the close co-evolution of information and communication technology with society. And then we need to combine that with the effort of Earth system science. So global system science makes current series of crises and disasters applicable to the solution of global scale problems, taking a massively data-driven approach. And it's attempting a grand integration of knowledge. That means it's highly interdisciplinary. And let me go through a couple of the fields I've been working in. So, opinion formation. As you know, there's been models of opinion formation. They're basically assuming that people would have one or two opinions, pro or contra, and that invites people basically to think about these opinion formation problems like spin systems. There's some controversy about these kind of models and whether physics can be really transferred easily to the behavior of people, and whether we shouldn't be doing more experiments to find out how people really interact. And of course, we should do that. But there's also continuous scale opinion formation processes where the degree to which people agree or disagree with a certain subject might change over time as they interact with other people. We've done experiments here published in PNAS that looked at how people estimated the solution to a factual question in response to knowledge that they got about the estimates of other people. And as you can see over here, there is a convergence process going on. So consensus is forming. But it doesn't mean actually that the average solution is actually finally better hitting the true value than in the beginning. That is kind of a surprising thing. So you've heard about wisdom of crowds. If you average over many independent assessments of people, that would often give a very good approximation of the true value. But as people interact with each other, it seems to undermine the wisdom of crowds. It's something now we really need to care about. And given that there is this consensus formation process, people have wondered, why doesn't everyone agree about everything? Why do we have so many different cultures despite this convergence process? And it is quite difficult actually to come up with models for this. So people have created bounded confidence models, but the assumptions are pretty artificial and also quite sensitive to the assumptions, because if you add a little bit of noise, then again you get convergence, and this is not what we find. Right, so what we basically did is we added some noise in such a way that it would reflect that people would want to be different if there are too many people agreeing on one thing. Kind of the desire to be individual, right? So everyone is dressed in a different way in this room. And that has a reason. And if we do this, then basically we can see that we have not only groups forming, but also these groups split up again, as we often see that for political parties too, that sometimes break apart into several pieces. And so that model seems to reflect pretty well what we actually find in reality. And the phenomenon might be compared with droplet formation in physics. Now, one of the questions that social scientists care about a lot is the so-called micro-macro problems. So basically to derive macro behavior, that means system behavior, from assumptions about individual behaviors. And it turns out to be not so simple. In economics, for example, people have often applied so-called representative agent models. In physics, we would say this is a mean value approximation that people have made there. So basically, you assume that people behave in response to average behavior. And it turns out that this is actually not describing very well what we see in reality, and so the representative agent approach does have serious limitations. But since a very long time, in fact, people have realized that the whole in society is not just the sum of its parts, it means the actions of the individuals. And this is really important. There are emergent phenomena that basically reflect that if many people interact, then something new can happen that was not intended by anyone. We'll see examples of this, but what comes to mind is, of course, group formation, group spirit, and all these kind of things. And what happens is that not only does the interaction create macro phenomena, but also what happens on the macro level feeds back on the individual behavior and changes the rules according to which people behave. And this is different from physics. So social science is not just social physics. It's not just a matter of having more data. And here is an example of an emergent phenomenon. So we'll see the breakdown of this fluid circular flow and the formation of the so-called phantom traffic jams. By the way, a nice experiment done by Iki Sugiyama, one of your colleagues here in Japan. And this basically shows that things can happen that nobody intends. On the contrary, everyone wants to drive smoothly over here. But something very different happens. And even actually, if we could read the minds of everyone, if we would really know everything about every single driver, that couldn't prevent the traffic jam from happening. Right? So mass surveillance, in a sense, is no recipe to get rid of this problem. The problem comes about because of systemic instability. There's a certain density above which small variations in the speed are amplified. And then basically that creates eventually stop-and-go traffic. We found similar stuff in our laboratory where we've done decision experiments with people. And we found an astonishing accuracy of a best response model. This is a deterministic model. 96% of people's decision could be predicted by this model. This is amazing for a social experiment, right? Still, the macro level outcome could not be predicted well, because this is what the model predicted and this is what happened. Very different, right? The question is, why is this happening? How is it possible that such an accurate micro model would not be able to predict the macro outcome? And this is because just a few little deviations can actually create completely different outcomes. And that's happening in certain kind of situations, in situations of systemic instability. In fact, that's what we have over here. Now comes the next surprise. If we add noise to the micro model, that means we make the micro model less accurate in terms of predicting individual behavior. The macro level predictions become much more accurate, right? So we wouldn't expect this. So it already shows you that just collecting more and more data about every individual is not going to necessarily improve your predictions about the future of society. So we need to do a smarter job as scientists. Okay, so why are these things happening? This has to do with complex dynamics as we find it in complex systems such as traffic, supply chain, social, political, economic, and ecological systems, but also in turbulent fluids. And we need to distinguish here between complex and complicated systems. A car is a complicated system, right? It's made up of many pieces, but it's well controllable. right? However, the interaction between cars is not well controllable by the individual drivers. So that is actually the reason why we find traffic jams, and we can find all sorts of complex patterns resulting from those interactions. Right? These are measurements of different kinds of traffic jams. And we know that also from weather predictions. Even if we had 1 million times more data, we could not predict the weather in 3 months' time exactly. Why can I say this? Because what is behind the dynamics is so-called turbulence, and we know the physics of turbulence, and there is a sensitivity to the initial conditions. That means no matter how accurately you measure, after some time, you won't be able to predict the further development. And there are other things going on in complex systems, the illusion of control. So, for example, assume you want to get here, you want to change the system. What often happens in complex systems is that for some time, even though you try hard to change the system, not much is happening. This can be pretty frustrating to managers and to politicians. Everyone is trying to change a complex system. So what you would do is you would try harder, yeah? And again, nothing happens. So you try even harder, and then eventually you get to the point where there is a sudden systemic shift, and the system behaves in a completely different way. Unexpected and unintended in many cases. So, another example is this over here. It's a simple Volterra system. It means a predator-prey system, basically. And we assume that there is a hunter that is trying to get the system towards this point over here. What happens instead is what you can see with these blue lines. You end up in a completely different place, right? So these complex systems behave in a counterintuitive way. And sometimes they self-organize very nicely, as you can see over here. There's these lanes of uniform walking direction. Opposite walking directions are separated from each other. And it doesn't require any traffic signs or policemen or law to tell people what they should do. They will just automatically separate as a result of the interactions among them. But if the density is too high, then trial disasters might happen, not intended by anyone. Again, the situation would get out of control. I've shown you this already, so I can skip this. But very similar problems occur in logistics systems, and you can actually do nice games, the so-called gear game will show you, and also even experienced managers, that it's really very difficult, if not impossible, to keep control of certain kinds of logistics systems. And we know that very well, in particular for the world economy, where we have actually booms and recessions. These kind of dynamics can be understood with network models and with delayed adaptations of production processes as they occur, of course. And then the model actually predicts non-periodic oscillations in the global output. And this is what we actually observe, right? So classical economic models for business cycles predict a periodic behavior of the system. And any deviation from periodic behavior would require the assumption of a shock caused by innovation. And I don't think this is a very satisfactory explanation, so I believe we can come up with much better models. And crime is another example where we find this unstable dynamics. Now, what makes things even more complicated, and in a sense worse, are cascading effects that we find in network systems. And some of these systems are even systems of systems. And that makes it even more complicated and makes the system, in many cases, also more vulnerable. So networking, of course, creates great opportunities, but also systemic risks. And we know that in connection with the financial crisis, but also disasters. So some years back, we looked into causal interdependencies as they occur during disasters. One event causes other events, and these cause again other events. And if you study things carefully, then you can basically see some regularities. And this kind of graph can help you actually to anticipate what might happen next. So you can do anticipatory disaster response. You can prepare much better if you know this. You don't have to be surprised by what happens next. And sometimes it even happens that one disaster causes another one, and you know that very well. So the last earthquake here has caused a tsunami and also nuclear meltdown. So unfortunately, these kind of things are more typical than one would think or hope. Again, because of these couplings between different kinds of systems. We need to figure that in much better in the future. And many models of risk analysis, in fact, assume that there wouldn't be feedbacks of things that happen in response to other things back to what happened before, right? And I think that can largely underestimate actually the risks in complex systems. So yeah, this is the kind of thing that can happen. If there is systemic instability, a single local perturbation, and it can be very small in fact, could trigger chaos in the entire system. So this is an experiment made to illustrate how chain reactions work. And we know that these kind of chain reactions are controllable in many cases. We know enough about them. But sometimes also things get out of control, as a nuclear accident in Chernobyl, for example, shows. And these kinds of dynamics can also happen in our society. Just most of the time it happens on a much slower scale, right? So these kinds of explosive events can extend over years. So we would not even understand this is something like an explosion. But such a thing has happened actually through the financial crisis, and it's still destroying parts of our economy and society. We know a similar phenomenon actually from cascade effects that lead to blackouts. We're seeing large blackouts in particular in Europe, and we're seeing this also in financial systems. So as a result of this increased interconnectedness in the financial system, you've seen a meltdown, you've seen cascade effects in the sense that the bankruptcy of Lehman Brothers has triggered off bankruptcies of many other banks, actually hundreds of banks, and that cost us hundreds of billions of dollars. So this is just one example, because we've also seen these flash crashes. So this particular one, May 6, 2010, actually eliminated $600 billion in just 20 minutes. You know. So that's something that was unheard of before. It was caused, as it turns out, by automated trading. So all those trading algorithms have responded to each other, and given there were enough that sold all sorts of stocks, others stepped in and sold too. In fact, some solid stocks of large companies turned into penny stocks. And that means the ownership of that company changed completely within just a few minutes. So this is amazing. And of course it's dangerous. And that's why we need to change these systems in such a way that they wouldn't show these destructive cascading things, right? And for this, we need to build in engineered breaking points. Actually, engineers have done that for many years in the electrical system, for example. So this is a really nice design issue. How would we have to design the financial system so there would be these breaking points in it? Okay, let's go back to social systems. And of course, these have been traditionally very complicated to model, partly because of lack of data. And one of the coordination problems actually leads to environmental exploitation or environmental pollution or overfishing. And this is called tragedies of the commons. When something happens that's not good for anyone. Before we get into the tragedies of the commons and social dilemma situations, let us look into this problem, a coordination problem. So assume two pedestrians walking in opposite directions. If they want to pass each other, then either most people have to step to the right side, or most people have to step to the left-hand side. Right? So two people, game theory say players, who have two options. Game theorists talk about strategies. In this case, left or right. And it turns out both do the same thing, then they succeed, that means there's a benefit of their action, which is like greater than zero. While if one goes to the right and the other goes to the left and they're still standing in front of each other, they haven't succeeded, there is no payoff. Okay, so this is the typical matrix for the so-called coordination game. And the question is, what happens in these kind of situations? And it's possible to derive equations for the change of the relative proportion of people doing one thing or the other. And these equations are called replicator equations that can be understood based on imitation dynamics. And if we plug in these so-called payoff matrices, then what you find is this equation over here. And it's easy to determine the station solution by setting this to zero. It turns out there is three different solutions. P equals 1/2, that means 50% go to the right, 50% go to the left. P equals 1, that means everyone goes to the right, and P equals 0, everyone goes to the left. Now, you'd perhaps think the 50-50 situation seems to be the most natural solution in these systems, but it turns out this is an unstable solution. That means the slightest deviation from this 50-50 situation will drive the system towards P equals 0 or P equals 1, which means that a behavioral convention will form, and either everyone stays on the right or everyone stays on the left. Right is the European solution, left is the Japanese solution. Both work well. Now, instead of the coordination games payoff matrix, you can play with other payoff matrix. And one that is particularly interesting is that of the so-called prisoner's dilemma. Basically, if both people cooperate, then it creates a benefit, a reward. If both don't cooperate, then so-called defection, they would get a very low payoff called punishment. If I cooperate and you don't, then it turns out you will get a very high payoff called temptation, larger than R, and I would get a very poor payoff S, smaller than P. And that means basically cooperation is risky and defection is tempting. And for this reason, cooperation, even though it's favorable, is unstable as this smooth traffic flow, and as a result, cooperation erodes and we end up in this unfavorable state that tragedy of the commons results. And the question is, what happens in different kinds of settings? So if you look at a circle of people interacting with their neighbors, and then add some links randomly, connecting them with additional people, that could be seen as a very simple model of globalization. Then what we see is that in the beginning, cooperation goes up, and so we would go on networking the system, right? And cooperation even increases, and so we network more until eventually it turns out, ooh, now cooperation goes down, 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 the more we network. And I guess this is kind of a problem that we're having. And it's something that I believe most politicians are not aware of, and most business people are not aware of, and even most scientists are not aware of. But this problem is there, and we need to find solutions for it. And that means we need to find suitable social mechanisms that would promote cooperation in situations where it would otherwise not occur. And in fact, this is something that people have been dealing with since the early history of humankind. And there are a number of mechanisms that people came up with in order to promote cooperation in societies. One of them is kin selection, or genetic favoritism, that means giving an advantage to your relatives. And we see that still in a number of Arabic and African countries, and also, in a sense, all over the world, because inheritance law gives accumulated goods to relatives. In Europe, we had dynasties and all this, and we have that here too. But there are other mechanisms. I mean, genetic favoritism also produces undesirable side effects like blood revenge and ethnic conflict and all these kind of things. So people have come up with new mechanisms like repeated interaction and friendship called direct reciprocity. Nobody has to die here. But too much friendship also might not be good because it might create corruption, right? There might be a difficulty for new players to come in. And so, again, people are trying to come up with better mechanisms, and reputation mechanisms based on indirect reciprocity might be a better solution. There are other solutions too, where people basically punish those that don't comply with certain kind of rules, such as social norms. It's called peer punishment. And in many cases, we delegate this punishment to institutions such as the police, and then it's called full punishment. Right, so the entire point is to transform the prisoner's dilemma into another kind of problem that allows for cooperation. And there are different kinds of transformations leading to different kinds of games, such as stack hunt game, harmony game, snowdrift game. And this is kind of the approach that we have. And in principle, there is no limitation in terms of other mechanisms. So really, the question here to the computational social science community is, can we come up with better mechanisms, right, for our future society? In fact, we've been working on such a thing. And one of the approaches that looks very interesting is merit-based matching, where people who show high levels of cooperation are matched with other people showing high levels of cooperation. And now, what it does is it's not only good for cooperative people, but also it creates a trend towards more cooperation. That is interesting. Now, competition also turns out to increase efforts of people. Competition can be combined with different kinds of mechanisms, and one of them costly communication. But we've also been looking into other kinds of problems. I mentioned punishment before. Punishment of non-cooperative behavior. And we find very interesting dynamics if we look at this in the spatial setting or network setting. It turns out, in fact, that we get just the opposite outcome of what we expect if everyone interacts with everyone else, or if everyone interacts with randomly picked interaction partners. That means the representative agent model predicts a completely different outcome from what we find over here. So the very fact that we interact in a spatial setting or in social networks makes a big, big difference. Now we've also been looking at the implications of success-driven migration. So what people often do when they look at spatial game theory, they assume that an individual would imitate the best performing neighbor's strategy. Now we combine that with some other rules. Okay? First of all, what we do over here is we add some noise, some strategy flipping. That means with a small probability people do something else than what is actually expected according to this imitation rule. And what you can see in this prisoner's dilemma kind of situation is that unfortunately cooperation goes away. Cooperation is shown in blue, and instead defection results. So even though everything started quite promising, it ends in disaster. Right? A similar thing happens if we add random long-term migration. So people distribute all over the world, and as a result, society falls apart, and cooperation disappears. Now, we will now simulate imitation plus those two noises plus success-driven migration, where we assume that people within a certain radius around them would look for empty places and try to identify promising places that would offer them a high payoff if their neighbors didn't change their behavior, which might happen. And then the question is, what happens here? What do you see? Will we end in cooperation or defection?
Cooperation.
Cooperation. That's a daring hypothesis, because my PhD students thought it would not even make sense to do the computer simulation. It would be a waste of time. But in fact, look what happens. So this time we start with defection only. In a very bad situation at the beginning. Then the course of migration, and people distribute over the world, and sometimes there's a random change towards cooperation for a short time. Then after a very long time period, we find that there is such a small island of cooperators that occurred by coincidence. And once that has happened, actually, cooperation spreads all over the world quite quickly. And this is amazing. That's something that we didn't expect. And in fact, it has something in common with nucleation effects, as we know them in physics. So you can see it over here. There was an undercooled fluid, and you just snip at this bottle, and suddenly the entire system changes, right? The question is, do such things also happen in reality? And that's why we did experiments in our decision laboratory. And in fact, it turns out mobility is key to success. Yeah? So payoff increases with mobility. Now, there's something else. Humans are not just selfish, it turns out. And that has puzzled economists for a long time. And the question is, why is this? I mean, in a sense, this model of the Homo economicus is kind of maybe a good reflection of people with Asperger's syndrome who don't care about other people who don't have social feelings, right? And these kind of people often say, those who do have social feelings behave in an irrational way. Now let's see whether this is really true or not. So economists have often taken it as a fact that people would be selfish, because if they were not, that's the idea, they would give advantages to others, and those others would have more offspring, and I would have disadvantages and couldn't afford to have so many offspring. That means non-selfish people would eventually disappear over a couple of generations, and selfish people would spread. I haven't taken that for granted. I said, okay, let's simulate it in the computer, let's check it out. And so let's see what happens. So the assumption that we made are the following. Agents decide according to a best response rule that strictly maximizes their utility function given the behaviors of their interaction partners, their neighbors. Now the utility function was assumed to consider not only the own payoff, but also to give a certain weight to the payoff of their interaction partners. And this weight is called friendliness, and it was set to 0 for everyone at the beginning of the simulation. It means everyone started selfish, unfriendly, right? Then friendliness is a trait that is inherited to offspring. And the likelihood to have an offspring increases exclusively with the own payoff, not the utility function. That means caring about others doesn't matter for your offspring. The payoff is assumed to be 0 when a friendly agent is exploited by all neighbors, and it means therefore such agents will never have any offspring. And finally, there is some mutation of the friendliness value, but we have specified it in a way that it would lead to pretty low friendliness on average, just based on this mutation. In fact, what we'll see in our simulation is that much higher values of friendliness occur under certain kind of conditions. So what are the results? Well, it turns out economists are right most of the time. In this area over here, homo economicus results. Everyone is selfish. But there is a small corner over here where other regarding preferences occur. Not just other regarding behavior, other regarding preferences. And this happens when actually the offspring are raised in the neighborhood of their parents and not in a random place. And this is what humans do. In fact, they spend about 20 years with their offspring, which is kind of unusual as compared to all other species. So there must be a reason for this, right? And in fact, these other regarding preferences make humans powerful because it makes them more cooperative. In fact, it allows them to overcome tragedies of the commons, which selfish people can. They will run into this tragedy. And so they would end up with higher payoff, but it takes about, say, 50 or 100 generations to get there, right? It's an evolutionary process. And then instead of everyone being unfriendly, you get this broad distribution of friendliness values, around 4 and 4, as I said before. And in fact, this is well compatible with what is found actually in experiments. These are experiments of my colleague Ryan Murphy. Yeah, it's true, there are some selfish people called individualistic here, but most people actually have some degree of pro-sociality. And in fact, this is known since a very long time. Even Adam Smith wrote, however selfish man may be supposed, there are evidently some principles in his nature which interest him in the fortune of others, and whether their happiness necessary to him, though he derives nothing from it. Just unfortunately, this insight didn't go into economic theory for a long time. Now, apparently, no, we need to change this. We need to be able really to reflect that most humans have social preferences. And here's a computer simulation. I'm not sure I have enough time to show it, but let me show the results. The results are here. So we assume two populations, different genes in a sense. And you can see that not only do they both get cooperative and develop social preferences over time, they also start to cooperate with strangers. This is just a matter of time. So we can learn this, right? And we need to learn this because otherwise we'll be in trouble on this little planet Earth. So what I'd like to say is that besides the Homo economicus, there's another solution, which is Homo socialis, and that requires a different kind of treatment, because as long as everyone decides selfish, that can be perhaps approximated to some extent by statistically independent decision making. While if people take care about others, then decisions become interdependent, and that creates complex dynamics. And that's why we need computational social science to learn more about these complex dynamics, right? Okay, and so besides this theory for Homo economicus, it's about time to develop an economic theory for Homo socialis. Now, people also differentiate in time. They become different since the early days, actually. And so they have different preferences. We saw that also in the simulation. And then expectations can clash. It can be difficult to come together in a sense. And so we need to come up with multi-population simulations. And here we have looked at two populations that have just opposite preferences. Population 1 prefers behavior 1, population 2 prefers behavior 2. The question, what happens in this system? And that depends very much on the reward that you get for showing the behavior you like, as compared to the reward for conforming with the behavior of your interaction partner. And depending on this, if you have different outcomes, so you could have a society where everyone does what he likes, and that's a fair society, or we could have a situation where population 1 sets the norm when it's in a majority, or where population 2 sets the norm. And again, we did experiments in the lab, and actually these different outcomes can be found in our laboratory experiments. And besides looking into stake hunt games, this is the case that we just looked at, you can also look at multi-population prisoner's dilemma games, snowdrift games, harmony games, and whatever you care about. And it turns out there are really a lot of different possible outcomes, and all those outcomes are found in our society. That means there's a very simple two-population, two-parameter model. You can understand cooperation, the breakdown of cooperation, conflict, revolutions, all of this. This is amazing. So we can get even analytical insights into this. And conflict is, of course, an issue that we all worry about. There are now more and more data about conflict in Iraq, in Afghanistan, and Middle East, and that allows us to get much better insights into what creates conflict. And one thing that matters is intercultural distance. And basically, besides the possibility of simulating this based on data, we can also look into different kinds of possible scenarios now with calibrated models. So we can learn something about possible solutions. This is interesting. And there are in fact several solutions, and one of them is segregation. The other solution is more tolerance, right? And it may depend on the cultural distance, whether one solution works or the other. And in fact, we know these multicultural problems occur all around the world. So what we've done in the past is we have basically enforced social norms by punishing people who deviate from social norms. And so this has created social order. Now it turns out in multicultural settings, this punishment doesn't create social order in many cases, but instead it causes escalation, conflict. Because one person would say, hey, you didn't behave properly. And another person would say, how dare you telling me how I should behave? I behaved exactly as my culture expects from myself, you know? And so that person gets angry at the other person and strikes back, you know, and then they start to quarrel, and in the end, things escalate and it ends badly, as we've seen in many places in the Middle East, Ferguson, and also the disagreements between Russia and other countries over Ukraine and also Syria and so on, and show that you have this multicultural problem, then punishment and sanctions are of course also a way of punishment, are not leading to a solution, it just makes everything worse. And so the question is what to do in a multicultural world society to stabilize social norms. And reputation systems, multi-dimensional reputation systems can do this. They would basically help you to decide, you know, whom to interact with in what way. So we need new solutions, we need new social mechanisms for this new world we are living in. Now, there's more and more data actually becoming available, and that's of course great and opens up new opportunities. And the Future ICT project has been pointing out to this. And the main components of this project were to create a planetary nervous system, to measure data in real time, a living Earth simulator, to do computer simulation, that's a computational social science activity basically, and then create participatory platforms that would allow everyone to use the benefits of these new approaches, and also to think about ways to accelerate innovation. And in fact, we were bringing together different communities, social scientists, engineers, also natural scientists, and we did that all over the world. More than 30 countries, I believe, in Europe, in the United States, Mexico, in Japan, in China, in Singapore, in South Korea, in Australia, and many places, really, Russia too. And unfortunately, in the end, the money didn't come, but the ideas survived and spread, and I think this is what really counts. And I'd like to zoom in a little bit in these different parts. So the idea of the planetary nervous system was really to get data in order to allow us to get a picture of the world around us. And in fact, now we can actually measure and predict conflict and how it spreads in the world. We can measure scientific productivity, flow of ideas. We can measure means and concepts, as we've done that in physics, for example. It gives us a very good picture of what happens in physics over time. And we can actually measure how cultures spread over thousands of years, just with birth and death data. And this is quite fascinating. So here, this video shows, for example, how America was discovered by artists. Now, living Earth simulator. So basically, with the data that's now becoming available, you want to be able to assess certain kind of scenarios that haven't happened, right? So for example, how resilient is European gas supply with regard to certain kind of political scenarios, right? And for this you need models and you need data. We've done that. We also looked into epidemic spreading, and it turns out that if we not just look into data of who fell ill in what place and what time, but also consider air travel data, then we can transform the data and represent them in a way that we could actually understand the spreading phenomenon as a circular spreading in effective distance considering air traffic. So then suddenly everything makes sense, and we can identify actually the source of the disease, where it has originated. We can also predict what would be the next cities hit by the disease. And so basically from the chaotic patterns that you see on the right hand side, we get towards a pretty clear pattern that we see on the left hand side. Right? And this kind of knowledge can be really used in order to improve the situation. So they're quite powerful epidemic simulators now that use data about populations and their mobility and infection rates and all these kind of things in order to make estimation of what happens, and then you can change certain kind of things, like immunization can be taken into account, whether you close down certain airports or not, and what is the effect of these kind of measures. And it turns out some measures that appear to be intuitively right actually don't make much difference, and the other measures are pretty effective. So this is pretty nice, and could be extended, of course, to bringing together all sorts of models, as I've shown you before, to build a living Earth simulator, to get a picture of what's going on in the world. Of course, in the beginning it wouldn't work so well, as we know that also from weather simulations. Early weather simulations were quite bad. We need to realize that, but eventually it became better and better, and now they're very useful and quite reliable for some time. But besides modeling this world, we could go a step further and model virtual world with different kind of decision mechanisms, different kind of financial systems, and you name it. So basically test out new social mechanisms and economic mechanisms before we deploy them on our planet. And maybe even build virtual economies in which we can earn real money, right? And in fact, interactive games are actually becoming important experimental platforms these days. Now, global participatory platforms, this is about involving people in the loop, giving them feedback about the situation they're in. And for example, there are now apps for your smartphone, anti-panic apps that will basically show you what is the situation at a mass event, what are the crowded places that you should avoid, and all these kind of things. And also the authorities would get an overview picture, not individual view, but an overall picture that allows them to act more efficiently. We can also use feedback mechanisms actually to overcome annoying congestion. So as this video goes on, we'll turn on a driver assistance system, and that driver assistance system actually manages to get rid of this annoying congestion, as we'll see in a few seconds. So now, even though the inflow stays the same, you can see that we have a free flow because we've changed the interaction of the cars with the driver assistance system. And yeah, I mean, I don't need to explain this to you. Cars become increasingly smart, and of course, we could build many kinds of assistants that help us in all sorts of everyday life situations.